Hi, folks. So, I'm Dr. Stewart, for those of you who may not have me as your everyday teacher. And I'm here today to help out the folks who had NWEA testing or are in any way confused on the texting and driving unit. This is kind of an overview of the major concepts of the unit as well as how to work your way through the spreadsheet. So I'm going to go step by step through the major concepts of physics that you need to know to complete this unit. And I'm going to walk you through the spreadsheet to make sure that you can do your summative task. So I'm going to share my screen and present to you. Here we go. Actually, I'm going to present a particular Chrome tab. So, going to start with the description of what is it we're doing in this unit. So, texting and driving, what does it all mean? Why are we doing this? Well, first, part of the physics standards is that you need to be able to design a solution to a complex real-world problem by breaking it down into smaller parts. So, when we're thinking about a complex problem, we want to consider, how do we solve difficult problems? How do we think about the scenario? How can we be systematic about thinking through a solution? And how do we define this system? How do we figure out, like, do I have to know everything in the world to solve this problem? Or what do I really need to know and just that? And so we decided to pick a topic that is relevant to your lives, especially as you become some of the newest drivers on the road. And so if you think about it, there's a lot of car crashes and there's a huge amount of injuries because of accidents from texting and driving. So when we say, oh, hey, don't text and drive, that doesn't necessarily sink in until we get the idea that 1 out of every 4 car accidents at this point is caused by texting and driving. So how bad is it really? Well, to know that, we need to know some basic physics terms. And this starts with speed. So speed is the rate of distance moved per second. So how far do you go? How fast? Velocity seems like the same thing. And in many ways it is. Velocity is speed, but it's speed with a given direction. So it's important to know. So here's an example that gives you the difference between them. So you're in an airplane, it's traveling at 500 miles an hour, and you ask the flight attendant to play frisbee with you. I don't think that's going to fly really, but c'est la vie. So you're traveling at 500 miles an hour, and you're throwing a frisbee at 25 miles an hour. How fast is the frisbee traveling? Well, you want to consider, is the frisbee traveling in the same direction as the plane or in the opposite direction of the plane? That's where velocity matters. We already know the speeds, but without knowing which direction you're throwing the frisbee, you can't actually answer this problem. So let's just say we're throwing it towards the front of the plane in the same direction. You would add these two numbers together. 500 miles an hour for the speed of the plane, 25 miles an hour for the speed of the frisbee. That's a seriously fast frisbee. Don't let that hit you in the face. So in actuality, that frisbee is traveling at 525 miles an hour because you add the two together if they're going in the same direction. You would subtract them from another, so you'd say 475 miles an hour if the frisbee was traveling in the opposite direction of the plane. So how do these things look when we start talking about them in physics? In physics, we love to use graphs. And so when we graph a speed or we graph a velocity, we're graphing distance over time. So which of these two is going faster? Well, to figure that out, I pick a point that's pretty easy to figure out. For example, this dot right here. It says that in 8 meters, it took 2 seconds to get there. So this car is traveling at distance of 8 meters and it took 2 seconds to get there, right? So distance over time, it's basically traveling at 4 meters per second. You divide them. You take the distance and you divide it by the time it took to get there. So this car is traveling at 4 meters per second. Now, the same car over here goes 2 meters in 2 seconds. So I divide my distance divided by my time, and this car is traveling at 1 meter per second. So 4 meters per second versus 1 meter per second, this car is going faster. It is going up that line, gaining distance, right? The higher up you go, the farther you've traveled in a shorter amount of time. Now, sometimes we don't start at 0. Sometimes we're starting the car when it's already traveled a certain distance. Let's say you started a car trip, but you had to stop and get gas. So you're not really starting at your origin point. You're starting from the gas station. And that's where you end up with this. So this is a very confusing slide. So I'm going to make it bigger and I'm going to make it as obvious as I can and walk you through the pieces. Every single thing on this slide means exactly the same thing. I know, kind of crazy, but I wanted to show you all the different ways we can represent this car trip. So, first of all, we could represent it with a picture. So you can look here and you've got a 0 point. This is where the car originally started and it went some distance, but then it stopped for gas. So we're going to start from after getting gas. So we're not really starting from 0. We're starting from 10 miles into our trip. So sometimes there is what's called the offset. The offset is how far you have already gone. So if I've gone 10 miles already, then I have to start where at 0 seconds into my trip from the gas station, I've already gone 10 miles an hour. Or sorry, 10 miles, excuse me. And so from there, I have to add 10 to all the rest of my numbers because I'm not starting from 0 and 0. How would that look on a graph? I start from 10, not down here at the 0 point. How would that look in an equation? I add 10. So in all these different ways of doing it, they all represent that starting from the gas station, I've already gone 10 miles. Now I have to look at speed. If I go at an absolutely constant speed of 5 meters a minute or 5 miles a minute, then here I have in 1 minute, I've gone 5 extra miles. So I started 10 miles out. Now I've added 5 miles. 2 minutes, I've gone 10 miles. 5 minutes, I've gone 25 miles plus my original 10 extra. So I'm at 35. So when I look at this line here, it's the same thing represented. For each minute I'm driving, I'm getting 5 miles further out. Minute, mile, up and up we go. This is called a linear pattern. It's also called a slope. If I look at this in the equation, I'm saying that I'm going 5 miles, this is distance, for every X number of time. And so The y is how far I go. And then this is my this is my distance times time. So this together is my speed. So how fast am I going plus how far did I start from? So looking at this down here, I've got a car. It started 10 miles out, and now it's going at a constant speed of distance times time, right? But the thing is, sorry, speed times time plus the distance I've already gone. And so I think that this equation is the easiest to read. So the final amount that I have traveled is if I take the speed that I'm going, and this is v for velocity because hopefully I'm going in the same direction the whole time. So my velocity times the amount of time that I've traveled plus the distance that I already had under my belt when I started. So how does that look on a graph? If you stick to a constant velocity, in other words, you're not changing speeds. We're not stopping at stoplights and then accelerating after that. Let's pretend like it's a wide open road, no stop signs, no speed traps. You would just be continually increasing the distance over the time that you're traveling. So we call that constant velocity, or you could think of it as the constant speed in the same direction. So if I were to think of that in words, I could say, I think as time increases, my distance traveled will, I sure hope in your head you just thought increases. And in what kind of pattern? A linear pattern, because we had that lovely line. So as my time increases, my distance increases in a linear pattern. But, and how would that look on a graph? Well, we just saw it right here. It would be a line. But we don't usually go at the exact same speed all the time, right? We usually accelerate. We get faster. And so if you were to figure out the equation for acceleration, it is your change in velocity. It's how fast you are changing your speed in the same direction. And you're going to measure that every second. And so the way that it looks when you write it out is your units in meters per second per second. So in other words, how much are you increasing your speed in the same direction in meters per second? That's speed or velocity in the same direction. So meters per second is the velocity, but how much is that velocity changing each second? So it's per second per second. Meters per second per second. Whew, what does that look like? It looks like this. We have a curving line this time because it's not one constant velocity along the way. That velocity is picking up speed. So I start off where I'm only going less than 5 meters in 1 second, but then I start speeding up. And so as I speed up, I'm covering more distance, which is the height, in less seconds. So as I speed up, you're going to see that as time increases, the distance more than just increases. In fact, when time doubles, distance quadruples. And how do we represent that? We represent that as an exponential equation. So here, the equation for speeding up over time is the distance we're going to travel is equal to 1/2 the acceleration multiplied by time squared. Now, I'm not going to get into the confusing details of why this is 1/2 acceleration. It has a whole lot to do with the good old Pythagorean theorem, and I'm not going to go that deep. Let's just say we can look at this and see, wow, my speed started a little bit slow, but over time, oh, it's going up. So as time is increasing, the distance that I'm covering or that I'm traveling is increasing even more. So as time doubles, distance quadruples in this example. And so what does that look like on a graph? We have the position of the car, right? So how far is it traveling in how much time? Well, from 0 seconds to 1 second, that's a pretty like low slope. You're not getting very far in that first second. But between the first second and the second, whoa, we just jumped up a lot. We went from 10 centimeters in 1 second to in the next second from 10 to 50. Wow, we've traveled 40 centimeters, right? The difference between that in that same 1 second. So we're increasing our acceleration. So the line is getting more and more curved upward as we're getting faster and faster. So what would it look to brake? Because we're talking about braking. So a graph of a car who's braking, well, you start out going pretty fast, but then as you hit the brakes, you're traveling less distance, which is the y-axis, in that period of time. And so as that line flattens out, you're going less and less distance over that amount of time. So the way we represent that in an equation is instead of talking about braking as acceleration, braking is deceleration, which is also known as negative acceleration. So the difference between speeding up and slowing down is throwing a negative in front of the number. So, can we interpret from a graph what a car is doing? Well, let's look at this first one. If the car is steady, speeding along at a fast rate, you got a straight line. That's constant velocity. That car is maintaining a fast speed. But what if the car was speeding along and then came to a dead stop? Boom. Let's say there was something in the road right here. And so slam on the brakes, crazy fast, instantaneous stop, which, is probably not entirely accurate. And then it's a straight line across. So over this period of time, the car has gone no distance at all. So that would be stationary. Then, if we had to reverse and go back to where we came, you're actually losing distance and it would go down the other way. So this would be a car actually in reverse. And then really what do most cars do? Well, they do something a lot more like the green one, right? So we speed up from a stoplight, we're going, we're getting faster. And then, oh, we got to slow down. There's another light, stopped at a red light. And so if we're curving up, we are accelerating. And if we're curving down, we are decelerating or braking. And if we're at an absolute line straight across, we are stopped. So a reminder of our why, you have this video linked into your altitude cards. I'm not going to show this whole thing right now, but this is where you get your answers for your spreadsheet, because inside this video, it gives you all the details you need. See how there's a number on the pavement here? As you watch the video, watch for these numbers because they give away whether this car is going to hit this guy. So using what you know about speed, velocity, and acceleration, is this friend going to hit his buddy because he was distracted by texting? So this is the end of my first segment, where we're now at a point where hopefully we have an idea of what the graphs mean. And so if you're still like not feeling entirely good about it, please look at your card from this past week where it says, you know what, I'll actually show you an altitude right now. Hang on. It is the card that says velocity and acceleration explained and practice problems, also known as synchronous class. And so essentially this card, and I'm going to just show you this right here. Hang on, let me share my screen. So this card here, you have it from each of your classes, has a video explaining speed and velocity in case I wasn't entirely clear. Same thing about acceleration. And now you have some practice problems to do. So based on what I've just explained and these lovely little videos, you want to complete this practice set no later than Sunday night so that in time for Monday, we can give you some more examples of that. Okay, so I'm going to stop there. This is our first component specifically on the physics of what you need to know for this unit. Now I'm going to do another video that is going to be, okay, so now that I know about speed and velocity and I can interpret these graphs, how do I do that spreadsheet? So the next video is on how to do the summative spreadsheet that goes along with this unit. I'll see you then.